Hello, welcome to Mickey Techie. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement of creating these kinds of technical videos in public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me as spark of creating these kinds of technical videos in public domain. And I would like to thank Almighty my God for my good health and broad mind. And I would like to thank my friends, followers, my dear students and subscribers for their continuous watching my video and commenting. Today's topic of interest is refrigeration and air conditioning. The refrigeration and air conditioning in modern era nowadays, these refrigeration and air conditioning is very versatile as well as very much needed equipment in householding applications. Generally speaking, what the refrigeration and air conditioning will do, it maintain a pre-specified or predetermined condition predetermined condition of a room or any closed surface or any closed region is maintained at the constant or predetermined pressure, temperature and volume. Like that it will do. Okay, so it makes us sophisticated, and it will give always a fresh and a very energetic condition to us. Mostly in householding applications, all the preservatives like tablets, vegetables, fruits are kept under a constant condition, temperature, pressure condition. So, in order to avoid the decay of foods, so preserving foods, the refrigeration plays a major role, as well as the air conditioning will makes us very cool and work effectively. So AC is concerned for us, whereas refrigeration is concerned for preserving foods. Like that, the the equipment specification will be done. Okay, let me go in detail about refrigeration and air conditioning. This both refrigeration and air conditioning will work on the second law of thermodynamics, and we know that the typical figure of a refrigeration is here. The refrigeration cycle in every one of our home, the refrigeration is like this. It is having a components like we start with the evaporator. Evaporator is the space where foods are being stored. So the evaporator coil, and from evaporator it takes heat and it goes to the accumulator and compressor. Compressor will give a pressure to flow the refrigerant throughout the cycle. So the compressor will make the high pressure and high temperature vapor refrigerant to the condenser. Condenser is a phase changing device. Condenser and evaporator is a phase changing device. The phase, either if it is coming in a vapor phase, it is transferring into a liquid phase. So that is the condenser will do. The liquid refrigerant will be in the evaporator. The liquid refrigerant is being converted into steam, a dry or wet vapor. Like that, it have to be change the phase. So after the condenser, the high pressure and low temperature liquid is passed through the receiver or storage device and passed through the throttling device, and further low pressure and low temperature refrigerant is passing through the evaporator, and the cycle continues for cooling the substance. Here you have to notice that the refrigerant should be have a less boiling point or less freezing point. For your information, that the properties of refrigerant is different. So that we have to discuss in forthcoming slides. And next is a AC. We know that this is the hot season. Now I am speaking 11th March. So 11th March 2021, and hereafter for the next 3 months we have a very good sunny season. So the outside temperature is bit higher than the inside room temperature, since the temperature is not at all tolerable. So we are making our room to the very sophisticated temperature, like at 25 degrees Celsius. Even though the outside temperature is a 40 or 50 degree, the inside temperature can be 25 degrees. It can be maintained by means of the air conditioning. So air conditioning device is very similar to the refrigeration device, where some of the components are being less. So here also the compressor is there, evaporator is there, condenser is there, and the expansion device is there, and the inlet and outlet both fans are having, and it will make very less temperature fall, whereas refrigerant makes a huge temperature fall. Even 0 degree or minus 5 degree can be done in the refrigeration, where in the air conditioning 16 degree is the maximum temperature which can be go. On the maximum up to 30 degree we can use this air conditioning. Okay, so with this information I go to the theory. So we know that the refrigeration and the air conditioning are derived from second law of thermodynamics. The refrigeration and the air conditioning and heat and mass transfer are the applications of second law of thermodynamics. We know that the second law of thermodynamics deals with the two statements, Kelvin Planck and Clausius statements, and both are giving a common point called entropy. The outcome of the second law is the entropy, the degree of disorderness. That we know that all the given input is not at all converted into output, where the law plays like that. So with this information I go with in detail about the applications. One such application is refrigeration and air conditioning. Today's topic is that. So I'll go with the refrigeration and air conditioning. Definitely we will see the heat and mass transfer for the next application of second law of thermodynamics in forthcoming lecture videos. Now we have three devices called heat engine, heat pump, refrigerator. Three are the applications of second law, the R and AC. And here the heat engine deals with the Kelvin Planck statements. The efficiency, thermal efficiency is the network input divided by heat supplied, network to the heat supplied. So that is the thing. Whereas if it is a reversible cycle, the thermal efficiency is 1 minus T2 by T1. And whereas heat pump and the refrigerator are both are the Clausius statement. These are the outcome of the Clausius statement. The heat pump and the refrigerator, we deal with the coefficient of performance, where refrigerator heat rejection is more than heat absorbed. That is the thing you have to notice, that in refrigerator heat rejection is more than heat absorbed. And the relationship between the COP and the heat supplied and heat rejection in a heat pump is COP is equal to heat supplied divided by heat supplied minus heat rejection, whereas for COP of reversible cycle is T1 divided by T1 minus T2, whereas the refrigerator COP is heat rejected divided by heat supplied minus heat rejected, where COP of reversible cycle is T2 divided by T1 minus T2. And we know that the relationship between the heat pump as well as the refrigerator, that is the COP of heat pump is equal to 1 plus COP of refrigerator, whereas the heat engine and heat pump are the efficiency of the heat engine into multiplies with COP of heat pump will come is outcome is equal to 1. Here you have to notice these points. The higher COP higher COP, lower will be the running cost. So if we want to reduce the running cost, we have to make the coefficient of performance is bit higher. So all reversible cycles have same COP operating between the same temperature range. If we want to increase an efficiency or a COP, we have to change the temperatures. This is more important. The COP does not depends upon the working substance. Which substance it may be, it won't consider that. The temperatures are very important. Heat rejection and heat supplies are very important. So Carnot refrigerant for cooling is 0 to infinity. Carnot COP of the heating, it is 1 to infinity. This is for your kind information. And next, the reversible engine operating between the thermal reservoirs of T1, T2 and T3, where we can take the T1 is higher, T2 is intermittent and T3 is a bit lower than T2. Let's take, we have a conditions. So the efficiency of the engines are same, that T2 is equal to square root of T1 into T2, but the work output of the both engines should be same. So T2 is equal to T1 plus T3 divided by 2. So the both reversible engines are coupled together, where the temperature of 1 is higher and temperature of 2 is the intermittent and temperature of 3 is the lower thing. Like that, the conditions will vary. Next, the refrigeration and air conditioning. Refrigeration produces lower temperature as compared to surrounding, where air conditioning working substance is air, conditioning is moisture air, which comprise of dry air and water vapor. So air conditioning means we are adding a moisture, we are adding a humidity to the dry air. So here the degree of freedom of the moist air is 3. This you have to notice that. Next is the refrigeration capacity, which is very important. The refrigeration capacity means making 1 ton of water vapor water to an ice in 24 hours. That is the 1 ton of refrigeration, or we can say for melting 1 ton of ice in 24 hours is the ton of refrigeration or refrigeration capacity. We know that 1 ton of refrigeration is equal to 1000 into 335 kilojoules in 24 hours. That is that comings into 1 ton of refrigeration is equal to 3.5 kilowatt, where which is equal to 210 kilojoule per minute, where 12,600 kilojoule per hour. The refrigeration capacity is equal to refrigeration effect into mass flow rate of refrigerant. So whereas the refrigeration capacity is equal to H1 minus H4 into M mass of the refrigerant, where H1 and H4 are the enthalpies at the stage 1 and stage 4, where COP is equal to refrigeration effect divided by work done into mass. So the refrigeration effect into mass, which is nothing but refrigeration capacity, where work done into mass is the power input. So we can make the COP is equal to refrigeration capacity divided by power input. Okay, next is the volumetric efficiency of the reciprocating compressor. We know that the compressor is a device which add pressure in the incoming flow as compared to outflow. So outflow is more pressurized and having more temperature than inlet condition. So the compressor, whatever may be the compressor, the low temperature, low pressure substance is being compressed and converted into high pressure and high temperature steam at outlet. So the volumetric efficiency of the compressor is mv1 divided by pi by 4 d square into L into N, where pi by 4 d square is the area. Therefore This equation can be rewrite as volumetric efficiency is equal to m dot velocity divided by m dot volume specific volume divided by ALN. So that we can give. Okay. So we know that m dot is the actual mass flow rate, d is the diameter of the piston, and v is the specific volume of inlet of the compressor, n is the speed, x is the number of cylinders. So nx means the number speed into number of cylinders. And volumetric efficiency, we know that 1 plus c minus c into P2 by P1 whole power 1 by n, where C is the clearance ratio, that is clearance volume to the swept volume, where P2 is the final pressure, P1 is the initial pressure, n is the polytropic index. Generally n is equal to 1.441, like that. The domestic or industrial refrigeration, the cycle is irreversible, where for idling purpose we take the cycle is reversible. Next, the air refrigerant working on reversed Carnot cycle. Reversed Carnot cycle means it follows isentropic compression, isothermal compression, isentropic expansion, and isothermal expansion. So these four things, these four cycles are being followed in the air refrigerator. So it is a reversed Carnot cycle. Therefore, coefficient of performance is equal to heat absorbed by work done, that is T2 divided by T1 minus T2. The COP of the reversed Carnot cycle may be improved by decreasing the lower temperature or increasing the higher temperature. In the two conditions, decreasing the lower temperature is very good as compared to increasing the higher temperature. This you have to understand. Next is the Bell-Coleman cycle. We can say all the air refrigeration working on Bell-Coleman cycle. This is also called as reversed Brayton cycle or a Joule cycle. It follows an isentropic compression and a constant pressure cooling and isentropic expansion and a constant pressure expansion. So like that it go. So I am saying that the constant pressure expansion, constant pressure expansion, isentropic compression, constant pressure cooling, and isentropic expansion and constant pressure here expansion, like that. We have to come like this. So the equation, the flow is isentropic compression, constant pressure cooling, and isentropic expansion, constant pressure expansion, like that. You have to go like this. So this is the PV diagram and this is the TS diagram. So the Bell-Coleman cycle is an air refrigeration cycle. How the air refrigeration is working, compressor and expander are coupled with the common shaft. So this is generally used in aeroplanes or rockets propulsions. The cooler and the refrigerator is be there for cooling the air. So that is the Bell-Coleman cycle, like this. So compressor is there, a warm air is coming and cold air is going, and the condenser is there, evaporator is there. So all the things are there. This is the vapor compression system. So vapor compression system is having with the compressor. Here the compressor vapor, and the compressor is a main device. Condenser and the evaporator are the things. The expansion is a isothermal expansion or a hyperbolic expansion is there. So this is the typical example of vapor compression system, and this is the typical flowchart of the vapor absorption system. In vapor absorption system, the main components are absorber and vapor generator are the important devices. Here there is no compressor at all. In vapor absorption system there is no compressor, and the COP of the absorption system is bit lesser than vapor compression cycle. So vapor compression cycle will have a better coefficient of performance, whereas the large cooling or large area of the refrigeration we use vapor absorption system. So that we are going to cover in one by one. So the figure you have to notice this. So first we go with the air refrigeration cycle. It is working on, we know that it is working on Bell-Coleman cycle. So Bell-Coleman cycle, this is isentropic compression, constant pressure cooling, constant isentropic expansion and constant pressure expansion. The constant pressure cooling, that is Q223, that is Cp into T2 minus T1, where constant pressure expansion is the 1 to 4 process, that is Cp into T1 minus T3. We know that COP is equal to T1 minus T4 divided by T2 minus T3 whole minus of T1 minus T4. So here, if it is the pressure, P2 by P1 is equal to P3 by P4. Therefore, coefficient of performance is equal to 1 divided by Rp power gamma minus 1 divided by gamma minus 1. Rp is the pressure ratio. Rp is the pressure ratio. So it is equal to 1 divided by P2 by P1 whole power gamma minus 1 divided by gamma minus 1. And I have given a relation between the temperature and pressure. So this you have to take care. Next is the vapor compression system. In vapor compression system, we go with the COP. COP is equal to Q2 by W. Therefore, H1 minus H4 divided by H2 minus H1, that is H4 is equal to H3 for vapor compression system. Therefore, H1 minus H3 divided by H2 minus H1 is the form of COP in terms of enthalpy. Here I am going to cover the effect of decreasing evaporator pressure, effect of increasing the compressor pressure, like that. I am going to give an subsets in the vapor compression system. So these topics are very important in any competitive exams as well as the interviews. If we are interested in increasing the evaporator pressure, what will happen? The refrigeration effect will decrease, COP will decrease, volumetric efficiency is decrease, where work done will increase. So work done is the heat we supplied, okay? So it will be increased. If we increase the condenser pressure, refrigeration effect will decrease, COP decrease, volumetric efficiency decrease, whereas work done increases. So since condenser and evaporator are the phase changing device, the change in pressure will not be considered as a part. Since it is a phase change, pressure remains constant. So that you have to understand. If we apply a superheating, what will happen? The refrigeration effect will increase. Work done is directly proportional to inlet temperature. COP depends on refrigeration substance, that is temperature. Volumetric efficiency will almost be constant. So what happen if we use subcooling? The refrigeration effect will increase, COP increase, work done remains same, and volumetric efficiency will remain same. So in vapor compression system, the best system for improving the processes or COP is the subcooling. If we introduce a subcooling to the vapor compression system, it will produce a very good refrigeration effect. The COP can be increased, work done for the same work done. We can increase these things, same work done as well as the same efficiency, volumetric efficiency. We can increase the refrigerating effect as well as the COP. Next is the properties of refrigerant. The properties of refrigerant is very important. So please concentrate on the properties of refrigerant. So the properties are high latent heat, high thermal conductivity, high critical temperature, high critical pressure, high heat transfer coefficient, and a low boiling point, low freezing point, low viscosity, low specific volume, low specific heat capacity. It should be non-corrosive in nature, non-toxic, non-flammable, non-explosive, low cost, as well as mixed with oil. Because the compressor, it will having an oil in oil, it is in the inbuilt, so the refrigerant should mix with the oil as well. Next is the cascade refrigeration. Cascade refrigeration means it is having more than two refrigeration. Two refrigeration, two refrigeration cycle will flows the cascade refrigeration system. So here the overall COP is COP of 1 into COP of 2 divided by 1 plus COP of 1 plus COP of 2. Vapor absorption system, the COP is equal to TE into TG minus TC divided by TG into TC minus TE, where TG is the generator temperature, TC is the condenser temperature, and TE is the evaporator temperature. So please make a note, there is no compressor in the vapor absorption system. Here the absorber or generator and the evaporator condenser. The three components are very important. The temperature in these three components will significance the coefficient of performance. Next is the air conditioning. So maintaining the desired internal atmosphere. So that is the function of air conditioning. So the functions in detail, the temperature of the air should be controlled, humidity of the air should be controlled, purity of the air, motion of the air, all the things are being controlled. As per the psychometry, the refrigeration and air conditioning deals with the terms like dry air, moist air, saturated air, degree of saturation, humidity, absolute humidity, relative humidity, dry bulb temperature, wet bulb temperature, dew point temperature, wet bulb depression, dew point depression, like that the terms are being given. So these terms we have given in a detailed description of the forthcoming classes. The psychometric, I'm going to give a definite lecture in the psychometry, so we will be clear about what. Okay, so here I would like to give a detailed description about the refrigerator. So we know that so this is the figure of an air conditioning. It is very similar to the refrigeration. So refrigerator have to be flow. Evaporator is a thing where the substance is being conditioned, so that is being in the evaporator. The evaporator should be in the room, so cold air is supplied at the outside. The fan will blow air in the evaporator, so the temperature is being convected uh, or conducted and as well as the convected through the air flowing. So on the outside we give the hot air at outside. So the components like compressor, condenser, evaporator, melting device, refrigerant flow, all are same. And this is the simple air refrigeration system. So air refrigeration system contains gas turbine and main compressor. So the aeroplanes are using this air compressor. One such important point is the compressor air is a refrigerant. Therefore, the weight of the total refrigeration device is being reduced. So the air in aeroplane, all the weight should be reduced, right? So we are reducing the weight of the refrigeration as well. So the ambient temperature of air and the ambient RAM temperature is being used for cooling the devices. So next, a very important law is the Deltons Law. So Deltons Law deals with the partial pressure. So here the barometric pressure, partial pressure of dry air and partial pressure of vapor are very important. The barometric pressure, which is the sum of partial pressure of air, dry air plus partial pressure of vapor. Here, the specific humidity or humidity ratio omega is equal to mass of the vapor divided by mass of air, which is nothing but 0.622 of partial pressure of the vapor divided by barometric pressure minus the dry air pressure, partial pressure of dry air, where relative humidity is denoted in pi, where mass of the vapor divided by mass of the saturated vapor. So like that, in terms of the pressure, pressure of the vapor divided by pressure of the saturated vapor. Degree of saturation, it is in mu, that is omega by omega s, where it is equal to pi relative humidity of pt, means barometric pressure, pt or pb, whatever may be, okay. Barometric pressure minus saturated vapor pressure divided by barometric pressure minus vapor pressure. So the enthalpy of the moist air H is equal to enthalpy of the air plus enthalpy of the vapor. So it is the next equation. It is the specific enthalpy, that is mass time of enthalpy. Next, the sensible heat factor. The sensible heat factor is the sensible heat divided by sensible heat plus latent heat, that is H3 minus H1 divided by H2 minus H1. The sensible heat factor is the sensible heat minus sensible heat divided by sensible heat plus latent heat. And the bypass factor is the ratio of actual loss to the ideal loss, where bypass factor is equal to T3 minus T2, Ts minus T2 divided by Ts minus T1, or we can say T3 minus T2 divided by T3 minus T1. The efficiency of the coil is again a ratio of actual gain to the ideal gain. So T2 minus T1 divided by T3 minus T1. We know that the efficiency of the coil plus bypass factor is equal to 1. Therefore, the contact factor is equal to 1 plus bypass factor. So with this, I'm going to stop today's lecture. So if you have any doubts, please let me know in the comment section, and I will put definitely in another video for clarifying your doubts. I hope you have enjoyed the refrigeration and air conditioning within a short span of time. I hope I have given enough knowledge about R and AC. So with this, I'm going to wind up the today's session. So thank you all. Thank you. Bye bye from Santhosh.